Now, previously we talked about Lewis structures. Now, this is when we said Lewis structures or Lewis diagrams. Now, we said hydrogen has only one electron, so most of the times it's surrounding the other elements, whereas we have other compounds, right? When you have different compounds, like let's say you have HOCl, you check the one with the highest electronegativity. Okay, you check the one with the highest electronegativity, then that becomes your, what do you call, your central atom. So highest En, which is electronegativity, becomes your central atom. Now remember, I said you must use the periodic table, the Roman figures, right? Remember I said the Roman figures, on the periodic table, which means abo 1, 2, 3. These Roman figures, what do they tell you? They tell you about the number of valence electrons that we have in that atom, number of valence electrons that we have in that atom. I hope that we still remember this. Are we still okay? All right, and then we said we would look at maybe questions on this. Now, can I please just quickly grab your ATP, which would allow me to know the ones you should have. Term 1, term 2. Where is that? Oh yeah, HOCl. Let me also grab a periodic table. We're definitely gonna need a periodic table. Here we are. Let me just copy this. Maybe just take all of it at once, because we're gonna use it. Now, when you go into the exam room and then you look at your periodic table, the first thing you must do is to make sure that you remember where your Roman figures are, and therefore it will allow you or help you write these structures. Now, for example, HOCl. If I wanted to draw a Lewis structure for HOCl, the first thing I would look at is that, okay, which one is the highest electronegativity? If I look for hydrogen, it is 2,1. For oxygen, it is 3,5. For chlorine, it is 3,0. So the highest electronegativity is on oxygen. So therefore, I must write oxygen. Then I'll write 1, 2, 3, 4, 5, 6. Okay, those are the 6 valence electrons of oxygen. Then I'm gonna, yes sir. Wouldn't it be chlorine the what? The central atom? No. The central atom is determined by the electronegativity. And here we see the electronegativity, ne? Perfect. So now, if I draw chlorine here, so I'll put chlorine here. Chlorine, remember, it has 7 valence electrons, which is what you just said, which is good. So because it has 7, it only needs 1 more so that it has 8. So that 1 more will come from oxygen. Okay, then from there they will form a bond. Right, then hydrogen is gonna come in this side because it has only 1, it comes there, and then they form a bond. So now, therefore, this structure now, when you represent it, you say oxygen will be bonded to a single bond with hydrogen and then a single bond with chlorine. Today we're going to talk about lone pairs. and bond pairs, and we're gonna count them. Okay, so how many lone pairs are we gonna have here on the central atom? Please, when you count lone pairs, you only count the lone pairs and the bond pairs on the central atom, unless if you have only two atoms of maybe of different elements, you see. But when you count them on the central atom. Your central atom is oxygen. So how many lone pairs do we have? How many bond pairs do we have? How many do you think we have, guys? 4 lone pairs. Okay. Yes, ma'am. I like your definition there, ma'am. Actually, a lone pair, right? A lone pair is the one, it's a pair of the same electrons, meaning it's 2 electrons from the same atom that are not bonded with anything else. So for example, yes, for example, you see here this one and that, these are your lone pairs. You feel me? Alright, and then the bond pairs will be this one and that one. These ones are the bonded ones, so they are also 2. Do we see this? Okay, let's let's look at HF. It's what? It's kind of what? Let me check. These ones are not nice. Let's look at BF. Is it B? Okay, let's start with HF. Obviously, HF, it will be H with one electron, and then F is going to be having 7 electrons. So now, how many lone pairs do we have? Three lone pairs, and then the bond pairs is 1. Bond pairs is going to be 1. Right, let's look at NH3. Let's look at NH3. Now for NH3, we're gonna have 1 nitrogen having 5 valence electrons. Remember, it has 5 because of the Roman figure 5. So we say 1, 2, 3, 4, 5. Then now we're gonna have hydrogen here. We're also gonna have hydrogen there, and then we're gonna have hydrogen there. So therefore, if we look at it, right, we have nitrogen that is bonded to hydrogen, that is bonded to hydrogen, that is bonded to hydrogen. Now, how many lone pairs do we have, and then how many bond pairs do we have? One lone pair. 3. 3, Maniero, 3. So it's 1 lone pair and 3 bond pairs. Right, that's how we look at them. There's this one I like a lot, BF3. I think it should be BF3. 1, 2, 3. Yes, that's the one. That's the one I wanted. A BF3. Boron. It's what? Boron trifluoride. Now, if we have boron here, it has how many valence electrons? 3. Okay, so since boron has 3 valence electrons, we're gonna say boron and then have 1, 2, 3. Now remember, we're discussing BF3. Now fluorine is gonna be having 7, so it will probably be the one to come and fill in here. If we check, though, right, fluorine has 4, the electronegativity is 4, and then boron is 2, ne? So one might argue to say, but fluorine should be your central atom. But the thing is that these ones that are just left with one thing, like one electron to make a full 8 electrons, they easily surround the other atoms, same as hydrogen, which is only just needing one. Okay, so that's why here we're gonna have 1, and then fluorine is gonna have the rest of the thingings, 2, 4, 6, and then the other one is gonna come here, and then you're gonna have 2, 4, 6, and then the other one is gonna come here, and then you're gonna have 2, 4, 6. Right, so that means boron will be bonded to F, will be bonded to F, and then will be bonded to F. Ne. So guys, how many lone pairs do we have? How many bond pairs do we have? Now, Miss Uri, you will tell me the bond pairs, and then say, how many lone pairs do we have? Mm-hmm. Okay. Okay. Yes, ma'am. 3 bond pairs. Okay. 3 bond pairs. And then say how many lone pairs? 9 lone pairs. 9. No, remember, there will be 0, say. How? Miss Uri, why do you think we have 0? Okay. How? Why do we have 0? It's because we focus on the central atom. You understand me? It's 0. Yes. You are. Yes, exactly. You see, are we clear there? Good. That's something you should always look out for. Speaking of which, right, let's go back to methane, which is CH4, right? I'm quite interested in what you would say about methane. Now let's look at carbon. It has it has 5, 6. It has 6 valence electron. It's 4. It's 4. Hey, these Roman figures. Right. Let's say 1, 2, 3, 4. And then hydrogen is gonna come there. It's going to come here. It's going to come here. And then it's going to come there. Right. Now, Miss Uri this time, she will tell me how many lone pairs we have. And then Mr. Kevin, I'm interested in the bond pairs. Right. How many do we have? Lone pairs. So you're saying we have 0 lone pairs. Okay. And the bond pairs, how many do we have, say? These 4 bond pairs. And that's absolutely correct. Okay, that's correct. So as a central atom there, you can see that there are no lone pairs, but then there are 4 bond pairs. Speaking of which, again, let's look at this particular one, OF2, ne? OF2. OF2. Now, when you look at OF2, remember I told you that fluorine has 7, it only needs 1, so it can easily surround another atom. So therefore oxygen will be surrounded. So we say 1, 2, 3, 4, 5, 6 for oxygen. And then now that it is like that, Fluorine will probably come here. It will probably come here, and then also it will come here, like this, like that, like that. Right, so this is OF2. Now this time Miss Uri will tell me how many bond pairs we have, and then say I'd like to know how many lone pairs we have. Mm-hmm. The lone pairs, say. Is it? Yeah, the lone pairs. Two bond pairs. Okay. Okay. There's two lone pairs. That's very much correct. Wonderful. So it's two lone pairs, and then it's two bond pairs there. Right. Now, that is okay, but how do we draw these ones? There are these controversial ones that you must know how to represent, right? I'm saying controversial because they behave somehow a bit different from the rest. How do we draw the Lewis dot diagram for carbon dioxide, CO2? Can you guide me through this? Yes. Carbon is central. Okay. Should I show it's for surrounding it, or it's for surrounding it? Okay. So I will have, okay, 1, 2, 3, 4. Mm-hmm. Mm. Mm-hmm. Okay. So should I put oxygen here? All right. Let me put oxygen here. Now it's gonna be 1 here, and then remember oxygen has 6. Um. Okay. Then this one is not bonding with anything. Mm-hmm. That one I can still just show it on this side, right? We'll work on your 2 projects. Yeah, this one. Let me see if I can just. Hope I'm gonna be able to write. That it should be that side. Okay. All right. Um. All right. No, I like that realization there. 2, 4, 5, and then 6. Okay. Then what's next now? Mm. Carbon here. Mm-hmm. 4. 3. Yeah. Mm. You two oxygens, yes. So should I put oxygen here? All right, let's put oxygen here. Let's have it having one bond there. 2, 3, 4, 5, 6. Right. Then we have CO2, right? Uh, yeah. How? This one joins with that one. No, it can't now because already there is a bond here. So I, for it to rotate, nyana, it's not gonna be possible. Ah, hey, this is called an unfinished project, eh? All right, yeah, let's also finish it. What do we have? We're shorting what? I think we're shorting oxygen then, eh? Where do we put it now? Right, left, down, up? On the right, right. Let me write oxygen here, then have this, have that, have this, have that. 1, 2, 3, 4, 5, 6. Now, our biggest problem here is that there are electrons that are hanging that are not, bonding with anything. We can't even call them lone pairs because for lone pairs you need two, isn't it? So that's a bit of a problem there. Um, so what we can then do, right? What we can do is to understand that carbon it behaves very very strangely. Since it can make four bonds, maximum four bonds, it means it can also do some other stuff like this. Do you remember that it's like this, right? It is four like this. When it sees that there is oxygen, what it does is that it can move this one here, then they form a pair. Then it can also move this one here, then they form a pair like this. Right. Once it does that, oxygen then comes. Remember that oxygen was 1, 2, 3, 4, 5, 6. You remember that? Then oxygen also, it agrees. It agrees to say, it's fine, carbon, whatever you want, same. And then this one comes here. Similarly, the other one will do the same thing. Carbon, like this, and then like this. Then now you have formed oxygen and then a double bond carbon, a double, because now it's a bond, and then it's a bond, so and then oxygen there. So now oxygen has 2, 4, 6, 8, just like it wanted, and then it has also 2, 4, 6, 8, just like it wanted, and then carbon also has 2, 4, 6, 8, just like it wanted. Then it's balanced. Are we clear here? Yes, the octet rule is followed here. It's followed. So how many lone pairs do we have? zero, zero. And then bond pairs, we have four. Perfect. That is it there. That is it. So guys, I know the structure for carbon dioxide is always a headache shame. So please just know it, ne? It doesn't change. If you have caught it here, it will always be like that. So you'll be fine. Okay. Now, what about this is my last one in terms of these Lewis structures. Not NH3. It's HNO3. How do you think we're gonna do this one? Yes, so we need the structure, the Lewis structure for HNO3. That's a good start. Which one is having a higher electronegativity? Oxygen, okay. Here's oxygen. Okay. It is 1, 2, 3, 4, 5, 6. But tell me something. Does it become a central atom even though there are three of them? Just a question though. Oh, okay, okay, okay. So what can be our central atom? Nitrogen, ne? Yeah, 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 okay. 1, 2, 3, 4, 5. That, remember, nitrogen has 5. Do you agree? Okay. Now let's go. Let's fill in there. Let's fill in there. Where do we write? Left, right, or down? On the left. Okay, let's already get hydrogen out of the way. All right. Oxygen. We have 3 of them. Oxygen. Okay. Let's have oxygen here. Or I can write the bond, the double one here is still fine, and then I put 1 here because it has 6. On the right hand side. Let me make it yellow. Yeah. Let's put 1 on top of the nitrogen. Let me put 1 on top of the nitrogen. Can I make a double bond there? Okay. Here, yeah. They must join each other. No, it can happen also, but then now, how do they join each other? Because now this, I don't know. I will have to move it this side because the rearrangement was done on the atom itself. Remember, carbon is the one that was rearranging itself. So even this one must rearrange such that um, the central atom, right, it can bond with it and have two bonds if possible. So I believe we'll be stuck if we do it like this, ne? But no, thank you so much for trying it out. In fact, you got one thing correct, though. You should know this is very much correct, ne? Just yes, just that the others, right? We just need to rework on them. Yeah. So what we can do here, right? Because it's a complicated structure. The nitrogen can do this. It can say, you know what, this electron must come here. You see, it has rearranged itself. And if it does that, remember that oxygen, it will come here and then it will bond like this, just like with the carbon, like this, right? And then after that, the 6 ones will be here, like this. I mean, the 4 ones will be here. So this one oxygen is done. Then the other oxygen comes here, and then it says, okay, I have 1, 2, 3, 4, 5, 6. Right? So let me write the 6 here. To say it has 6 there. Okay. Then that space, who does it leave it for? For the hydrogen. the, for the hydrogen. So now it's gonna become like that. But it's quite interesting, because you see these ones, right? Sorry for that. So you see this part, it's a double bond that was already waiting for the oxygen at electrons, just like here. Remember, when you have the double bond for carbon, it then waits for the double bond from the oxygen, from the double electrons from the oxygen. So this one, it was already waiting for the oxygen. You see, while here it had to form it. Nitrogen had to form the double bond so that oxygen can also come with the double bond. Then here it was only one, and this one normally just does that. So therefore you'll have this double bonded to O, double bonded to O, single bonded to O, single bonded to H. What a beautiful structure. Oh no. Do you see it? Is it clear? Okay, perfect. So that is how we deal with that, in terms of looking at those structures. So if you know those, right? My last one that I know they like also. Sorry guys, my last one that I forgot about is this interesting one. You'll also help me to sketch it. HCN. HCN. How can we draw the structure for HCN? Mm-hmm. Mm. Nitrogen. Let's make it the center. 1, 2. Sorry. 1, 2, 3, 4, 5. Yes. And then rearrangement in the nitrogen. Yes, the nitrogen can rearrange, the carbon can rearrange. Okay, let's do that. Mm-hmm. On the right, okay. Let's put hydrogen there. Mm-hmm. Mm-hmm. You're almost done. Yeah. Well, what you would what you would say is that maybe carbon would do this and then maybe do this. Ne? But for it to do that, for it to rearrange this part and also rearrange this part, that one, it does it best when there is a double bond that is going to come there, you see, especially from the oxygen, just like we had previously. So in this case here, what carbon will do, right, it's gonna cater, because um, it can also do triple bond and then one here, so that one will be for hydrogen and then the remaining will be for nitrogen. Ooh, what a beautiful structure. HC triple bond N. So this is called hydrogen cyanide. Name hydrogen cyanide. Please, guys, these structures that I'm giving you, know them by heart. If you know all of them, then there is nothing that is out of the ones that is outside the ones I gave you that is gonna come. All of those that I gave you there are the ones that are going to come. Can I show you an example of a question paper asking on this? Right, so that we can see how do they ask the questions. Let me just grab any paper two. No, paper two. Just take a screenshot. Where is that? Where is that? Aha. A whole 17 marks. Imagine. Okay, let me do this. And I like the fact that they ask about your favorite friend. Your favorite friend. You want to see your favorite friend? Let me show your favorite friend. This is the one. What do we have there? The first statement. Hydrogen cyanide, isn't it? Yeah, they tell you that it's a very poisonous compound that is used in manufacturing of plastics, mining of gold, and as a poison. It's even used as a poison. So, what is a chemical bond, right? Um, what would you say is a chemical bond? Chemical bond. Chemical bond, it's what? Mutual attraction between two atoms, right? Mutual attraction um, between two atoms resulting from resulting from simultaneous attraction between their nuclei. Okay, simultaneous attraction between their nuclei, meaning between their nucleuses. That is what is a chemical bond. As we said, remember, a chemical bond is formed by the forces of attraction and forces of repulsion, but that mutual attraction between the atoms is what we call a chemical bond. Now check 2.2.1. What do they want? Yes. Yes, Lewis diagram. The first one is for hydrogen cyanide, isn't it? So now I know that you know that it's gonna form a triple bond, this carbon here, and then one bond with the hydrogen. So here it forms triple bond with nitrogen, like that. Then you get your 2 marks, ne? At least inyana, you know that I am coming out with my, yeah. You know why it's 2 marks? It's because I've already given you all of them. So when it's just a matter of writing the one they are asking, so hence it's not a lot of marks. You understand me? Right. What about H2O? This one you also know that we're gonna have oxygen 1, 2, 3, 4, 5, 6. Here it behaves very well, Shame. And then you will have this as your Lewis structures. So that is your 2 marks. That is your 2 marks. Is this okay with us? All right. Now, then in terms of the shapes, you're gonna the shapes you use the valence shell electron repulsion theory, which is the VSP what, but that one I would like us to talk more about it. It's a table that we must know, that is having these shapes. Yeah, but we'll talk about it in more detail. And then what is the electronegativity difference? But by the way, for 2.3 though, this molecule there for 2. Is gonna be just a linear, right? But once we discuss them, you'll then understand why. And then 2.4, the electronegativity difference for the CN bond, meaning for this part, for this bond, what is the electronegativity difference? So the EN difference, guys, it's simply saying that you must get the higher electronegativity minus the lower one, isn't it? So for carbon, what is the electronegativity? And then for hydrogen, what is that? Two. Is 3,0. So we say 3,0 minus 2.5. So our answer becomes 0,5. Right. Now, we have to understand that if our electronegativity difference is 0, if our EN difference is equals to 0, then it's a polar covalent bond. No, it's a non-polar, sorry. It's a non-polar. But then if it's maybe between 0, so let's say it's between 0 and it's what, 1,2, then it's gonna be weak polar. And then if it is between 1,2 and 2,1, it's gonna be strong polar. And then if it is equal to 2,1, or if it is just greater than 2,1, then it's gonna be ionic. So this is something that we must just remember there. So this one, they ask you for 2.5, what is the polarity of this HCN molecule, but guys, there is a difference between the polarity of a molecule and the polarity of a bond. If I were to ask you here, the polarity of this, the polarity of the, because we calculated for Cn, eh? So the polarity for the Cn bond is weak polar. It's gonna be weak polar. This one is the polarity of the bond. It's talking about the polarity of a bond. But then we have the polarity of a molecule. Now guys, polarity of a molecule, again, I'm gonna need us to talk about it when we discuss the shapes of molecules. Then it will make much more sense. Then here we have a table that shows values of the bond length and bond energy in the HCN. Now I want you to check. Here's bond length, here's bond energy. Bond length, bond energy. Remember what we were talking about. So for 2.6, it then asks you, explain why the bond energy of the CN bond is more than the bond energy of the CH bond. What would you say? (2.6) it says, explain why the energy of the CN bond, CN is 890, why is it more than the CH, whereas the CH is 413? Oh, and let me just try. You see? Aha. Aha. Well, if you answer it that way, ne, to say the bond energy of Cn is more because it has a longer bond length, well, it wouldn't be, remember we said the shorter the bond energy, the stronger is the bond, and therefore the higher the bond energy. Shorter bond length, remember, shorter the bond length, the stronger is the bond, and then the higher is the bond energy. Right. But then look at here. For Cn, the bond energy is 890, is very high. You would expect that the bond length must be lower, isn't it? Now but it has higher bond energy and higher bond length at the same time, which contradicts what we were talking about. Why could, what could be causing that? That's what they're asking. It's tough. Okay, the answer lies in the Lewis structure itself. That's why they are saying focus on HCN. HCN. Look at the CN bond. Look at the CN bond and then look at the CH bond. Do you see that the CN bond is a triple bond, while the CH is a single bond? So that is the explanation there that you will give. You see that the CN bond is a triple bond, while the CH bond is a single bond. So that means you will need more energy to break the triple bond. Are we clear? Yes. And then now explain the difference between bond length of the CH bond and bond length of the CN bond. Now here's where you're focusing on bond length. To say which one has a longer bond length? CN has a longer bond length, right? And then that is why. Why is that? Ne? Because on it should be that CN has a shorter bond length compared to CN. So the thing is that you will tell them that CN has a higher bond length. It has a higher bond length compared to CH. Compared to CH. Now the reason for that is simply because when you check CN and CH, hydrogen is a small atom, right? Where so this will C, and then if you check C, nitrogen is a what? Is a bigger atom. So just because it's two big atoms that are bonded together, they're gonna have a longer bond length, and this one is gonna have a shorter bond length. Do you see that? Can you see? Right. So we're saying that comparing carbon bonded to hydrogen and carbon nitrogen, the thing is that nitrogen is a bigger atom because it has more valence, it has more energy levels compared to hydrogen, which is just one energy level. So since hydrogen is small, it's gonna have a shorter bond length. Because what is bond length? Remember, is the distance between the two nucleuses, ne? Yes. Whereas the CN bond is because N is a bigger atom. Okay. So when you find contradiction from these things that we talked about, shorter bond length means higher bond energy and stuff, your explanation should not be about shorter bond length. Your explanations should be number one about the number of the type of bond. Is it a double, single, or triple? And then when you're explaining between bond length again, you don't have to always stick with that. You can talk about the size of the atoms so that you understand why does this one have a longer bond length, why does this one have a shorter bond length. Are we clear? Right. And then this will probably answer it very much clearly when we have talked about the shapes of molecules. But otherwise, guys, I hope that in terms of how bonds form, bond energy, and then Lewis structures, electronegativities, I hope guys were getting a grasp of how to answer these questions, eh? Yes, it's chemistry. Chemistry needs you to explain a lot and see what they are doing there. I will then try to send a, maybe also ask people on this so that you can just be answering there. Is that okay? Okay, perfect. So I will then see you guys next week on Monday. All right. Have yourself a great weekend. We have meds on Monday. Oh no, sorry, life science on Monday. Yeah, but then we'll have meds on Wednesday. We're gonna add more days, guys. Just especially for this May now that you're gonna be writing. We're gonna have more sessions, so please just prepare for that. Ne? Okay, thank you so much. Any question before we go?